How are you going? We're going to have a quick look at the basics of NRG Zone and looking at the principles of operation inside, and then we'll move on to some system installation and again system principles. Then we'll move on to some advanced system designs that I think you're going to enjoy, because it makes a breath of fresh air as far as I'm concerned into the imagination that you can apply to your system designs. So we'll get started and see what you think. Everything that I have to say will be based around this part of heating systems, that is, where a pump is either pumping from an open system going to zones, and then the fact that air should have been removed at that stage, and that we should be pumping from the neutral point, and that the pump's action, the force from the pump, should be moving towards the zones. So my name is Harry Ray. I'm with Energy Awareness, and I'll bring you through this, but I'd like to think that if you have any questions that you wouldn't be put out to contact me and ask, or alternatively any positive suggestions or any suggestions that you think would be beneficial that I can add to the comments or otherwise. So again, we're talking about the effect of the pumps drawing from open systems, from sealed systems, and even where you have a combi boiler, you still have a common area, you still have the pipe that exists delivering heat to the zones for distribution, whatever. So it's fair to say that manufacturers have always recognized that whatever about the pipe sizes leaving the manifold, that the pipe, you might have 22 mil or 28 mil from a boiler, maybe 32 mil, but the fact is that you might be delivering a lot more kilowattage or power than that pipe size would take if it was to be run around the job. And likewise, when it gets to the header situation, where manufacturers would recommend that if you have a 32 kilowatt, or sorry, a 35 kilowatt boiler, just suppose, that you would go all the way up to 1.5 inch header to carry that heat at the very least, right? There's a reason for that. You don't want the zones, a given zone or a group of zones, to be drawing so much flow that they cause it to pass another zone that needs fluid. So you want as little resistance as is possible within the flow and return headers. The governing factor that we would work with would be a minimum 0.3, but hopefully 0.2 of a meter per second traveling with inside in the header. 0.3 is fine. And that means that there's no resistance to flow inside there, so the zones can draw away easily, and as well as that the boiler can deliver in. So 42 mil or 1.5 inch would suffice for 35 mil boiler output. If we had a 70 kilowatt boiler output, we might decide that or with two separate boilers, or it doesn't matter. If you had one 70 kilowatt boiler, then the pipe size might be 42 leaving the boilers, 28 from each boiler just getting out of the boiler, into just where you're going to your header, you might have 42 1.5 inch, but in the header it's always recommended at that kilowattage that you would have 50 mil or 2 inch pipe. So a 2 inch header, 2 inch return header, and flow and return. Deaeration again is a very important thing. But we look at all this. The reason you might have a flow temperature sensor is that if the boilers had a sequencing or a weather compensating ability, that you would be able to take a temperature reading back into the boilers to advise the boilers what's going on with the system, so that they can modulate or a cascade as necessary to bring on more or less boilers if there was a sequential boiler arrangement. So again, if you count up all of your heat loads, you add them together, that's going to be the power of your boiler. Of course, you're going to add on 10 or 15% for pipe heat losses and the like of that, but generally speaking, here we're off with that principle. I'm not suggesting that any one of those zones should not be hot water, or that hot water might be added with a hot water priority situation, which we can talk about. But just now we're taking that there are 4 different zones or 3 different zones, doesn't matter. So we're focusing at this point in time on the 54 mil header or 2 inch pipe header for 70 kilowatts. And when low loss headers were introduced, the first reason they were brought there is that at that time boilers were generally not condensing, heat pumps were not normal, and so the last thing you wanted was condensation temperatures heading back into the boiler that would cool the surfaces so much that they would affect the flue gases and cause them to condensate, where the condensation would be slightly acidic. It would be sulfuric based if it was on the or sulfur based if it was from oil, or it could be hydrochloric acid and the like from LPG. So it was always a good idea, so with the low loss headers or with any arrangement, that you would have either a bypass from flow to return to cause the water not to be too cold, and with the low loss header that you mix some of the hot with the cold. But of course, in this advent of heat pumps and condensing boilers, the last thing we want to do is heat the return water, because if you're heating the return water, you're preventing the extra efficiency that comes from through heat pumps and condensing boilers from the condensation idea. And condensation can be upwards of 25% additional heat gain depending on how it's organized within the system. So it's a substantial thing to ignore. To my mind, putting in low loss headers and systems that do not allow for the maximum effect from separating the hottest from the coldest is contradictory to the fact that you want the most efficient system. Likewise, when the zone is taken, or zones are taken away heat, if they're getting some of the return water, they're not going to be delivering as much energy. If they're not delivering as much energy, then clearly they're not being as efficient as what they could be. And in that scenario, the zone efficiencies drop, the boiler efficiencies has to drop if you've prevented condensation or the proper COP of a heat pump. So therefore it can't be a good idea. I wish someone would tell me if I'm wrong, but I've never read or heard anything different than what was originally proposed, that low loss headers and the like were for. No one has ever said that they were wrong in what they said and changed their minds. So then people talk about buffer tanks, but a buffer tank is basically like all metal devices, same as the energy zone, is a dumb device. It doesn't know what's going on. If you have a connection at the bottom and that connection is connected to the boiler or heat appliance, then the coldest water that's lodged at the end of the buffer, because of stratification, will be drawn back into the appliance, and therefore you have a very good chance of having proper efficiencies in the system. But if you think about it, on one breath a manufacturer could say that you need the stratification for their boiler to work with a buffer, and then the same manufacturer might be selling a low loss header, which contradicts the whole point of what we're talking about. Now, if you have an energy zone, you certainly have the stratification because the heat from the appliance or appliances comes into the top chamber, which we'll go through, and the return water coming back from the zone go into the chamber here that I'm identifying the return chamber, but you'll see in a while that not necessarily so. But in this standard ordinary example, the coldest water is in the bottom chamber. That's what's collected by the appliance and brought back to the boiler. So you have stratification by the natural fact that hot water is less dense and therefore lighter, and you have the heavier water at the bottom. But you also have waveguide plates or separation baffle plates that prevent the hot water from getting towards the colder water until it's past each of the zone opportunities. The zone opportunities could exist in any chamber or any connection off the top port. And likewise with the return, the cold water can't be shunted back up to meet with the top water because of three principles, because of stratification, because the plates are preventing it, and also because the water has been taken away from the bottom zone area by the boiler or boilers that are connected. So you have all the benefits, like you've got your cake and you're eating it, you have all the benefits of a buffer tank, and yet you've got a fraction of the cost and a fraction of the size, and you also have the additional ability to have multiple ports that can be used for many different reasons. Inside in the energy zone, it's very simple. The most important thing to note is that there is an open path if water flows in from this connection and around this V-shaped baffle here that I'll show you clear in real images. Passes outside this pipe that delivers the heat from the right hand side. So it comes in here, flows across, offers itself to each of the zones, goes through 100% open bypass and goes back to where it came from if it was going back, say for instance, to a boiler on the left hand side. You could also of course have a boiler come in on the right hand side, flow through this pipe that traverses the unit, hits the center of this V-shaped baffle, turns back on itself, and as it travels back goes again over the bypass and can go back to where it came from. But you can also bring a flow in, say top right hand corner, go in travel left to right across the baffle, having left the pipe, and down, and then go to the bottom left hand corner. And also just the same, it can go in the top left hand corner, travel across the top chamber, the flow chamber, down through the 100% open bypass, and back at the right hand side. So it's extremely versatile for piping connections. You can actually do more than that, but we're just talking about the starting basics, let's say. So if we move on, we see, so where the hot water comes in from a boiler, if it's to be piped in this method, and don't take it for granted that this is the only method, because it's certainly not. You can do a lot more. But the normal, ordinary way, the most frequently used way that we come across, would be the flow brought, say, in at the top, and then this first zone will take some of that heated water away, do its heat delivery work, and the return is brought back to the bottom chamber. Likewise, the flow delivers to the second and third pump, so they can take away their respective heat loads and deliver the return water, the coldest water in the system, or the coolest, back to the return chamber, depending on where the heat source is. There is no reason why you can't have a boiler on the left and a boiler on the right. So each zone has an equal chance to get at the heated water. But the pipe here, let's call this a 28 mil pipe, is delivering a 28 standard round pipe delivers in. When it gets to this area, this is a rectangular area because the box itself is rectangular, the energy zone is rectangular, and then you have this waveguide or top baffle that forms a square to rectangular section. And if you were to measure the cross-sectional area of that and relate it to the area of the pipe delivering in, even excluding the diameter of the pipe that travels through the unit, you'll find that it is 3 to 4 times larger. This area is 3 to 4 times larger than say the inch pipe delivering. It's actually the equivalent of a 2.5 inch iron pipe or a 65 mil internal diameter pipe. So the water is going to do a couple of very, very important things. It's going to split when it hits the V-shaped baffle and go left and right if it's coming that direction, or it's going to split up if it comes through this pipe where a boiler delivering on the right hand side, and then when it hits the inside of the V-shaped baffle, again it splits and breaks into the volume of the bigger pipe. But because the bigger pipe is such a larger diameter, the water slows completely. The laminar flow that would have come through the pipe from the left or right will now travel always in a scattered flow from left to right, and any air in the system will be inclined to lift up towards the top, be trapped and taken away. So this is the primary air vent, but when I say primary air vent, I'm going to show you there's actually more involved. Also, you'll notice that if you were using this for a vent, the connection distance between the vent socket and the socket beside it, which might be used for a cold feed to a system, say, is only 75 mil. And again, that's another governing factor with regard to neutral point. If you have a neutral point in the system, it's where all of those combined zones are commoned into this chamber, and that chamber is open to neutral point, and all of the returns coming back are collected in this lower return chamber, and they're connected to neutral point. So therefore you can categorically say that this area here is the neutral point of the system, and that's where expansion should be taken in, where cold feed should be taken in, and where all the neutralizing effects of all the positive effects that are required for a proper system are located. So if it's neutral here, because the boiler pump is delivering in and the boiler pump is drawing back from there, and your expansion and cold feed are joined here, you've got the most perfect location to create a very healthy circulated heating system from that location. So this pump can draw from the neutral point, this pump can, and this pump can. Likewise, the return goes back. So let's focus on the port identifications, or the port IDs, the letters that identify the ports in any orientation. So we've spoken already about the flow coming on the top left L1, or also the flow could come in on R1, the right hand side R1. But just let's talk about, first of all, the IDs. As I say, L1, L2, L3 are the ports on the left hand side. L1 is the flow in this situation, R1 is the flow in. L2 and R2 have very useful roles to play. For example, if you're taking heat in from a boiler on the left or the right, and there's a surplus of energy that you haven't used to zone, so it's hotter water, and you want to use that energy to go back to, say, a conventional boiler like a loss-headed wood to have a high temperature return to the boiler, for instance solid fuel, for instance pellet boilers, for instance wood chip boilers and like that, and you don't want it to condense. This would be a better option to take your return back. You can, if there's no other boiler on the system and you want to use this as your return, it will work as your return, but common sense will tell you it will work better if you have a condensing boiler and you take it primarily from where the coldest water in the system. So we've spoken about L123 on the left, R123 on the right. The top 1, 2, 3 are kind of common sensible. T1, T2, T3. There's something I'd like you to note as well. The distance between T2 and T3 is about 75 mil, and therefore the difference in pressure inside the unit from here to here under T2 and T3 is very nominal, very little. So if you had an expansion in here and a cold feed in here, the differential between the two of them would be sufficient to have a huge effect on not pitching, because the problem with having cold feeds in a different part of the system to expansion is they're affected differently by maybe the primary pump or whatever, and it can cause pitching. So that's just a useful thing to know. The L3 and R3 are connected directly to the bottom chamber. I'm going to qualify what I said again. So is A2, B2 and C2. So you can also use those for returns if you want. Any return can be interchanged with any zone. So I could have, well, let's talk with the bottom connections. A1 and A2 form a logical circuit. Pump may be on the flow, a non-return valve on the return, and you're off. We'll talk about the non-return valves again in a while. B1 and B2, another logical circuit. C1 and C2. There is absolutely no reason why you can't come out of A1 and go back to B2, or come out of A1 and go back to C2, or you can come out of C1 and go back to A2. You can interconnect whichever zones you want, provided you're drawing from the same chamber. So if you think about that, the return R3 could be a return back point from a zone leaving A1, because it's just a matter of which chamber have you selected to be the flow and which chamber have you selected to be the return, and how you're using your bypass chamber. So let's move on again. Now we have the reverse. We've decided in this scenario we're going to introduce heat into the A1, A2, B1, B2 and C1, C2. So the flow would go in the A1, deliver heat up to the top chamber, and now we're using L1 to take away the heat to, say, let's say hot water or whatever, and we might use R1 to head off maybe through a mixing valve to heating zones. So it's completely up to ourselves again, but now we have heat introduced at A1, B1 and C1 from 3 respective boilers, and returns typically would go back from A2, B2 and C2. If that is the case, your zones are then taken from L1 and L2, or R1, sorry, being your flows, and L3 and R3 being your returns in conventional piping. Please remember, that does not mean you're stuck with that every time. This is just the standard way to go about the job that most people would be inclined to do. It suits most jobs. So now we have a different scenario. We get the manifold, and let's say we put it on the wall, and we actually pivot it around the center point so that the zones are looking upwards. And now we're going to take our boiler, say for instance, in at the top. So if we're taking a boiler heat into C2, well, it's going to be in the top chamber. So if I take heat into B2, it's going to be in the top chamber, and A2 top chamber. Whereas if I'm drawing heat back to boilers that are fitted directly above the manifold, my return would be now using the bottom chamber in this scenario. But if you remember that, the bottom chamber we originally called the flow chamber when it was pivoted up the 180 degrees the other direction. So the flow chamber is correct to call it, and the bypass chamber is always going to stay the same in the middle. And the return chamber, it's correct to call it a name when you're dealing with a job. But in a given job, the flow chamber might be the exact opposite to the typical or to the last job you did. So the flow chamber, instead of being a physical geographical point on the unit, is actually where the heat is introduced into and the heat is taken away from to deliver heat to the zones. The return chamber is where you would take the heat away from back to your boiler, but that you bring your returns back into. So here you can see we're reversing the whole scenario here. We're now saying that what was the flow chamber question mark is now actually the return chamber. What was the return chamber on the top question mark is now the flow chamber, where you're delivering flow into and taking it away from. So again, the naming of the zones is completely up to yourself, but we would still refer to it, just for our own usefulness, we would refer to the flow chamber as the one that is next to the vent sockets and whatever like that. But again, your discretion. The whole point of this talk is to tell you there's no absolute rules. The only rule that does matter is that when you put heat into a chamber, you take the heat from that chamber. When you take return water back to a chamber, that's where you return back to your appliance or appliances from. So now you looked at the diagram, the line diagram, and now we're going to look and see that in fact it's a kind of a replication of what's inside in the unit. Of course, this line diagram is showing 1, 2, 3, 4 zones, and this manifold is only showing 3 zones. But the reason I show them to be different things is that in reality the zones have the exact same effect no matter how many you put on. The sides have the exact same effect. Obviously there's a left and a right hand side, but remember we've also made obscure shaped units to suit particular purposes, and in that situation we can if you ever required that kind of a strange device for a very awkward boiler house or whatever, we'll create a shape to suit whatever you want, and we'll create flow chambers, return chambers, whatever. So instead of being stuck with a very awkward boiler house, you make the manifold suit the boiler house, and then you pipe directly onto the manifold, and you've just slaughtered the labour content and the confusion aspect of what would otherwise be a very typically a ugly looking boiler house that you're trying to figure out. You get your work done inside the manifold. So you can see, so there's a similarity with the two. I will now draw your attention to the air trap at the top of the unit, because when the water slows down as it passes across the top chamber and the air collects at the top, that's where the air is released. If you see, I'm now saying so that if the water slowed in the top chamber, the air rises to the top of that chamber. There's a sequence of baffles over here that funnel the air out through this middle of the 3 connections on the top, and that would be the opportunity, the best place to take air away. Once the air gets funneled in towards this socket, there's another baffle that kind of blocks it here. If it happens to make its way over that because there's so much air in the system, well, so what? There's gaps on the left and right hand side of this back baffle that let it flow back and still go up the vent chamber, so it makes no difference. But when we're talking with the air, there's more than the fact that the air is traveling here, because in each of the chambers there is a cavity created at the top of each of the chambers that actually acts as another vent trap, let's say. So you can see there's one here on the return, there's one here on the bypass, and each of those will catch air. There's a gap where the metal is not welded on the inside. It isn't enough to cause any serious amount of heat to drift through, but it is enough to let minute micro bubbles of air continually pass up until all the air is gone, so that they finally reach the top chamber and are released by the air vent. So in effect you have an elongated, very useful, very long air trap, and if the air isn't caught on the way out, when it comes back from the zones it's caught again, and if there's anything coming back or trapped in the middle chamber, they all allow the air to drift up to the top chamber. So that's why it's so rapid and so effective at deaerating systems. So it's not just confined to this little corner. Now the reason we refer to NRG 4, 5, 6 and so on, NRG 10, is that we have connections on the left, say here, call that one set of connections, connections on the right, and 2 sets of connections underneath, so NRG 4. With this one we have connections left, right, and 3 sets of connections underneath, NRG 5. And guess what? We have 4 sets of connections underneath, 1 on the left, 1 on the right, NRG 6. So if you had 8 sets of connections underneath, and 1 on the left and 1 on the right, you would call it NRG Zone 10. what we would actually say is, say for instance we had 50 mil on the left, 50 mil on the right, and 28 mil underneath. By 10 we would say energy zone 10, 50, 50, 28. If there was a difference in the ones underneath, which of course you can do, you tell us what you want, we'll make it to suit. You might have different numbers to represent the zones from left to right, and we manufacture according to that code. So it's very straightforward. So you can see that the diagrams are represented by similar shaped units doing exactly the same thing as the diagrams do. And now you can also see the massive open bypass over here. So the question is asked, what is the resistance through the unit? Of course it has a resistance, because everything is that in any way restricts water flow. It needs to be calculated into resistance. But what I'm saying is that the pipe delivering has a certain resistance. If you allow for the same length pipe passing through the unit, you won't be wrong, because there's less resistance passing through the unit than there is in the pipe delivering to the unit, because it's 4 times bigger and the water has a very open path, and the bypasses are completely much larger than the pipe delivering. Now you can see just close up here, we have the flow coming in, we have the returns going back to our boilers on the left or right, or cross flow if we wish, and then you can see heat being drawn from the top chamber through a respective pump with respective pipe sizing, so that you can set your flow rates for the first zone to be different to the second zone and third zone or whatever. Each one of them have equal access to the hottest water. Each one can deliver back to wherever you want it to go. This is just an example of one of those configurations. So now you can see how with a thermal imaging camera that, for example, as this system is starting to heat up, there was an issue with this job, because what we noticed is that the heat from the return coming back here, this pump was set too high and the boiler pump wasn't set high enough. By turning it on, we could see immediately there was some bypass water, water going backwards up through the bypass. So we were able to turn up the boiler pump a bit stronger, and you really don't care what's happening once it's below this level here. It's this point here that you want heat to. Anything beyond that doesn't matter, because it's flowing that direction anyway. So if we go to the second now, but you can see that there's a temperature coming here, 63.9. There's about 50 degrees at the bypass, and we're down to 44 here because some of the cold is being recirculated, whatever. But then when we rectify the problem by sorting the pumps, the bypass temperature might stay around 47ish, that's fine. 65 on the wind, but now look at this lovely 39 degrees, so we've got a very good 25-degree drop across the system as it's heating. We now can use our hands directly onto, carefully obviously because it's above 60 degrees, to touch the units, and you can actually detect where the temperature is. So by putting your fingertips carefully at the different surfaces, and you can actually hold onto the flow and return pipe to a given zone or to the boiler, you can check your differentials. Another very useful thing is one hand on the flow pipe coming in from your heating appliance, one on the flow going out to each zone. Are you getting the correct temperature out? If there's an issue, you'll find the difference. Your hands are incredibly accurate with regard to detecting even the slightest temperature sometimes. One very useful thing I noted during my career was that if you catch pipes with 59, 58 degree water, you certainly won't hold on to it, but there is a time you're not going to be doing any much harm. If you catch 60 degree water, if you catch a pipe with 61 or 62 or 63, you will let that pipe go very fast, because that is the temperature that the damage is done, let's say. But it's just a very useful bit of information. Try it if you've got a temperature measuring device. You find that you're not comfortable, but you can get away from 58, 59 up to 60. You rush away from temperatures above that. So when critical point of system design is where the expansion or pressure vessel is located and where the cold feed is located. So we're looking at three things here. We're talking about the way we would go about a combined expansion, or not combined as such, but a way to use the cold feed that is independent with a connection to expansion. We're talking about pressure vessel location, and we're talking about cold feed location. The target for all connections to open to atmosphere points is the system neutral point. We've already said that the perfect system neutral point, you can't get any better, is where the pumps draw from and the system is collecting the heat and where both of those meet, but also then of course where you bring in your cold feed. The cold feed is open to atmosphere, and therefore if the water has any kind of a, let's say, a negative force, the water will move down in the tank, and if it has a positive force, it will move up in the tank, or vice versa. And the same applies to the expansion. Remember, the water level inside in the tank is the same water level inside in the expansion pipe, so in effect they can kind of oscillate up and down to suit whatever's going on in the system. But because, as I said earlier, the two of these connections are about 75 mil apart, it isn't a great issue, because you'll find there's very, very little pressure differential here, and you find when you do it this way, the water barely budges in the system whatsoever, and that's extremely useful. I want to come to a very important point, and that is the cold feed connection to a heating tank. 99% plus of the time you find they're brought down and they're brought directly onto the top of a pipe or top of a connection, and then that allows the heat to drift up the cold feed pipe and form a one pipe circulation. By that I mean the water touching the wall of the pipe will be cooler and start to tumble. The water going up the middle of the pipe will form a circuit, and it'll tumble within itself, within the pipe, upwards till it reaches the tank. If hot water gets into the tank, it starts to convection currents around the tank, where the cold water, the hottest water goes to the top, the cold is drawn back, and in a very short period of time your expansion tank is hot. If your expansion tank is hot, what's going to happen is pure common sense. It will evaporate. If it evaporates, fresh water has to come in through the ball valve, and here you have the scenario that everyone wonders, how the hell are all of these systems getting gunked up with rubbish when there's no leaks and where the pumps are not whatever, and it's because the cold feed is in the wrong location. So we would always and never recommend that you put in a heat lock loop that travels down below where you're actually going to go to, turn back up. In fact, I'm showing here maybe visually about 200 mil. I would strongly suggest at least 350 mil if you can have at all with your cold feed loop down. That prevents, almost definitely prevents any heat drifting down and back up to the tank. If it is starting to go to the tank, the amount that's traveling will typically be radiated away from the surfaces of the cold feed and won't actually reach it. So now, where the cold feed comes up, it's vented, so it wouldn't be trapped as it makes its way down into the cold point, into neutral point. It's vented by the simple T connection across onto the expansion. And again, that's going to make sure that if any water pressure is causing the expansion to pitch over, it's going to be neutralized across, let's call it now, this bypass situation. So you find that with this scenario, the water level in the tank doesn't budge, and there's a simple trick to show and prove how well your cold feed and expansion is. You scoop some water from the heating tank into a clear vessel like a glass or a jar or whatever, and you immerse that the outlet of the vent pipe into the water, and then you get someone to turn on whatever pumps could be turned on the system, turn them on, and after a while turn them off, and you observe the level of water in the glass. If the water pushes into the glass, you've got water moving up the air moving up the expansion, which is a problem. If the water pulls out of the glass, you've got a problem as well. There's something wrong with your neutral point and where you're connecting your cold feed and expansion to. If you do with this system, the water in the glass does not budge. It actually stays precise. If it does budge, you're talking half a millimeter. So it's extremely good at making sure that you don't end up with all this gunk in the system that people are trying to figure out how to get out when there was no need for it to be there in the first place. If the cold feed and expansion is right, if there's no leaks in the system, and if the neutral point is created where the pumps can draw water from, delivered with the pump pressure acting only on the system and coming back to the neutral point, you find that the system stays unbelievably cleaner and last for years and years. Now when we're looking at a pressure vessel, the pressure vessel wants to connect to this target area again. So the center connection, R2, is a great place to put it on. But of course, T3 is a very good place. Even T2 is good because look, it's connected directly to the neutral point. And you couldn't very well have pressure here and like 100 or 120 mil or 200 mil away that you have no pressure here. They'll equalize. The same applies. You could go right around and into the L2. The reason is that this round pipe that would be connected to L2 is just connected to a square pipe here, which is still conducted directly over on to the target area. So your expansion vessel will have a direct impact on the system neutrality if it's connected to those points. where you bring your cold feed into a system for a pressurized system. I know it's only used for filling, but the benefit is if you do bring it into these points, the water can tumble down over the gap here, fill the system, the air is leaving, being pushed off out, and again you find it just fills the system extremely quickly. And it can vent the system very quickly. You typically find when you put on an energy zone system that unless there's something mad wrong with the pipework, if the pipeworks are put in anywhere reasonably right, rising towards the radiators or rising towards any high points in the system, and then you'll find that the core system vents itself in 1 minute, 2 minutes maybe maximum, depending of course on the size of the job, but typically they're extremely rapid at eliminating air from the system once the water contents are in. I don't mean that you can fill all the water into a system. I'm talking about deaeration. So now we're looking at where could you connect zones to a system, or heat appliances to a system. So you could take your return water from the coldest chamber, the return chamber. You could go to the bypass chamber because again, look, you've got a big opening here. So yes, you could take your return here down into your pump, around through your heat source and up. You can go directly into the top chamber here, but if you go up over and get rid of the air, you're also in the exact same place because that and that arrive at exactly the same place within milliseconds of each other. So, but also take into account that this could be an appliance, with this being the return, and this from the return chamber being a separate appliance. So if you had two pumps here and two separate flows here, you could have two appliances connected to the same side. I won't bother repeating what I just said because on the right hand side, because it's just literally a replication. The returns come from the return chamber or the bypass chamber, and the flows go into the top chamber. But you could potentially go in here. I strongly suggest that you wouldn't. You would bring your flow all the way over here so that the water carrying any air will be trapped in the air trap. You could bring it in here and it'll be pulled by the zones as well. It will actually work here. Don't get me wrong, it will work. I would not do it if I had any other choice. I would always try to get the heat over from left to right, whether it's through that pipe or in from the left or into this connection. To my mind, that makes much more sense. If you're putting boilers underneath the unit, you come from the lowest chamber, deliver heat up to the top chamber, lowest chamber up to the top chamber. So here now we have 3 boilers collecting heat. In fact, you could, if this dotted line was a 4th boiler, you could have 4 boilers, provided that the heat being delivered in can be taken away by the connections on the right hand side. And remember, this connection and this connection are right next to each other, so there's no reason why you can't tee them together. And this connection and this connection are right next to each other, so there's no reason why you couldn't tee the 2 of these together. So you could in effect have, let's say, a 28 mil pipe here, 28 mil pipe here, and go up to, because it's such a short distance, go up to even a 50 mil pipe here and take away the heat from 3 or 4 boilers if the pipe capacity and the resistances that you calculate are able to do the job. So just because you have inch connections, you can combine the connections and take much more heat. Same thing applies on the right hand side. You have a boiler flowing in through the pipe that traverses the unit, delivering to the top left hand corner, or you can go over to the top left hand corner, and again you have your multiple boilers underneath, 2 on the zones drawing from the cold chamber, delivering into top chamber, from the cold chamber, top chamber. So all of those are delivering heat to the top chamber, and that heat could be taken away to the left. This, of course, manifold has nothing to do with that. Manifold is just showing opposite ways of connecting boilers. Now if we take and we want to turn the unit upside down, we want to face it upwards. So remember what I told you, you would now have to use what would have been originally described as the flow chamber, but it's now the bottom chamber. You collect your return water here, and that's taken back to the respective boilers, and then the heat from the boilers is delivered into the top chamber. So that would be showing 3 boilers connected from left with a common flow output and a common return heading off to our zones. Another trick is that if you had inch connections here, there's utterly no reason why you couldn't go, say, with an inch by inch and a half or inch by inch and a quarter nipple, iron nipple threaded into here, and go immediately to a bigger pipe size, because the resistance over these sockets is not worth talking about. So you can take a much bigger volume of water away even from a standard unit without having to go to a bigger size unit. You'll actually find it would be cheaper to go to the bigger unit with regard to socket sizes, because it costs more for the fittings and the labour than it does to just get the bigger unit. So we do make units that have bigger connections on the side. The ones we're referring to here are kind of standard NRG 4, 5 and 6, which would typically all be 28mm or 1-inch connections. Again, the right hand side, nothing to do with this left hand drawing. It just shows that you can take boilers above the unit and on the right and feed off to your left for zones. Otherwise it's a replication of what I've just said. So if we take it now that we have zones, if we have our heat coming in at the right hand side here into R1 and coming back from say R3, we can then take zones from this point over to a pump from T3. It would be, you could actually take it from T2 if you have a vent on T2, but you pump towards the vent, you never put the vent behind the pump. And you can, and you also like from T1 through a pump and you pump towards the vent. So now you're delivering down to a zone here. You could have a zone taken from here. You could have two zones again. Look, 1, 2 with the dotted lines or whatever you want to call them, and then the solid lines. You could have another zone 3, 4 with a standard unit. So we've taken a boiler in here, and we could have 4 or even 5 zones if we had to. If you look at the pipe configuration here, and the same applies if you feed a boiler in to the left hand L1 and out at L3. You can take multiple zones on the right hand side, again just showing versatility. Now we'll very quickly move through this job, and it's to show the function of how the different ports and chambers work. It's an example only. If I have a heat pump and a gas boiler, I can take the flow from my heat pump into the middle chamber, and the middle chamber passes this opening here, which will allow heat to be drawn up if the zones are pulling water. So if zone 1 is taking heat, or zone A is taking heat, and zone B is taking heat, and the heat pump turns on, then the heat will be delivered in from the heat pump across the chamber. There's something I want to say to you from the very start. The brown color you're looking at here is not temperature, it's density of flow. So if you have a high volume of flow, the program that did this interpretation of what's going on shows it to be a darker color, and the lighter color would show very, very little water activity, say up around here, because the water is being pulled up here from the heat pump, flowing in, flows straight across the bypass chamber, sucked up into here, taken down on the zones. This is taking less flow than that because obviously pump sizing or pipe sizing is different, and so this has taken the majority of the flow. And then the return comes back in here, and again you could see the dark color heading back to the heat pump. So the heat pump is using the bypass chamber to feed heat in and feed the zones from that, right? Now, because we're doing that as well, you find that the air is pulled up, and the air will be caught and pulled into this area, so it'll vent away very well at the same time. If we go to the next scenario, we have the heat pump is turned off, and this time we are connecting to a gas boiler. But as I said to you, you don't have to take the return from the bottom chamber, and in this situation it makes more sense to suggest that you would take it from the middle one, because now you'll see in a while why, but like if the cold water is being collected from the zones here, it's pulled up out of the middle chamber into the gas boiler. Let's put some figures on this. Say the heat pump had been taking back 40 degrees and heating it to 45 degrees, so our 45 degrees would have been coming here. And now let's say this is the gas boiler says to go from 45 to say 65 with a 20 degree drop. So the heat is taken out from the zones and then is heated to its delta T macro that you've decided. It's put across the top chamber, and it arrives at this point. It's taken down at the same flow rate that the zone requires, because the zone pump determines what's going to go through that connection. Same with this zone's pump off out here, and the cold water is brought back up in, and you can see here that it's actually drawn across and off out and into the gas boiler. So if we move on and we look at the scenario where both appliances are working. So now the coldest water is coming back in the dark purpley color here on A2 and B2 into the bottom chamber, and then down into the heat pump, around the heat pump, across the middle chamber, immediately before it gets to the zones picked up by the gas boiler, raised to a higher temperature and delivered in through the internal pipe to the top left hand corner under T1, and then it feeds across and supplies the zones. And so the heat pump is now being used to preheat the gas boiler. In other words, from what we've just seen, you can have the heat pump on its own, you can have the gas boiler on its own, and you can have the two of them working in perfect unison to deliver where you're preheating to a final output temperature that you decide based on your temperature, your pipe sizing, your pump sizing. So here we have the scenario. You can see the water being taken back by the heat pump, delivered back in here, straight across, straight out to the gas boiler. The water was moving at a much wider space here, so even though it's a lighter colour, it's because the flow rate, or not the flow rate, but the volume of water moving is in a bigger area, but then it's concentrated here as it passes through the socket, so the speed increases, and then it's delivered at the same rate that's passing here. It has to pass here, and now you can see the heat being taken away again. We're going to go one step further, and we're going to add a little dimension that's very unusual but very useful. Before we decide to head across to feed our zones, we want to put on a hot water zone taking the highest temperature water. So because the hot water is coming in from the gas boiler here, when it's collected at this point, it can be taken by the gas boiler flow up to the coil of the cylinder, heats the cylinder, and the return comes back into the unit from the cylinder, and therefore it allows the cylinder to operate at high temperature, whereas the heat pump is still delivering in here, and depending on how much water the system is taking away, you could allow for enough for some of the water to be taken back up here from the heat pump alone. But it comes down to your calculations, your pipe sizing and your pump sizing. But again, you can have an additional high temperature cylinder up here, even though you're feeding it through preheating from the heat pump. Now we'll just have a quick recap on what we were talking about. If your heat source is on the left hand side, you could have a mixing valve and a pump arrangement on A1, A2. You could have full temperature with the pump drawing full temperature water out at the B1 and B2, and you might have full temperature off the right hand side where the flow is being taken through this pipe in reverse order, what we're talking about, and the return coming into the bottom chamber taken back by the pump. So you could have heat source on the left with multiple temperatures. The one on the right is where you might decide to have multiple heat sources. You might have, say, a heat pump or a condensing boiler, say for instance over here, and then you might, if you want to use the middle return connection, you might have solid fuel or a pellet boiler. The flows would return into here. This is just a different way to do it to what I showed last time. You do not have to go by any one of the pipe examples I'm showing, because each of them are different and independent in their own right, and have their own reasons why they're better in certain circumstances. So there is no fixed rule except that you take from the chamber you feed into with hot water and with return water. Now in this scenario, so we have a mixed temperature zone on A1, A2 and a full temperature zone on B1, B2. In this scenario, we're taking a controlled temperature into the manifold. So for example, if this was coming from another manifold or from something that is a high temperature boiler or whatever, and at the same time we want to mix the temperature down before it gets to zones, we might have, say, 80 degrees over here being mixed down to, say, 50 or 60 degrees here, and then the return is going to be, once the manifold is hot, the return will bypass through this valve and circulate within the chamber, and therefore if you have, say, an underflow zone, it'll reduce the temperature again, just suppose for underflow, because this is a further step down. You could have your full reduced temperature on B1, B2, and you could have full reduced temperature as well directly off the right hand side, so you can have a mixed temperature input arriving at the NRG zone. And likewise, you could have a full temperature coming in, and you can take away a controlled temperature to, say, another manifold or whatever you want, to a air handling unit or something on the left hand side. So where you put the mixing valves, how you locate the pumps, completely again up to your own imagination. I show this because it's a very useful function. Where, for example, you have a drifted heating on one side, say a solid fuel stove is delivering 10 kilowatts, say the job is 30 or 40 kilowatts. So you haven't enough volume leaving the solid fuel stove, but you want to distribute the heat between all the zones uniformly. You could introduce this very useful shunt idea, and that is where the water is pushed beyond this baffle, around that pipe and around in the circuit, so that all the zones have an equal chance of getting at the lesser amount of energy coming in from the stove. So your actual high temperature might be in a low volume, and this shunt pump will overcome that scenario and allow every zone access to that higher temperature distributed among the lot. Your return water is not compromised. That's the difference. Even though you're shunting water and you're dissipating the heat from the solid fuel or whatever you want and from your gas boiler, your return water comes back from the returns and is not mixed with the shunt water. I don't know of any other scenario where this system works so well. It's a very unique and an extremely useful solution in particular jobs. We've used it many times with really great effect. Now, if you, again, just showing that if you did have your flow coming in, I did say to you the flow chamber is going to be at its hottest. The heat will drift about, but of course it won't be as hot down here. You've seen that from the flow diagrams a while ago, but as such they would be warmer, whereas the return chamber is this lovely cold water that you're striving for with condensing boilers and heat pumps. So you can have your mixed temperature, full temperature in say zone 1 and mixed temperature in 2 other zones. Very simple. Again, people say cost. Cost to whom? Because if you're talking cost to the installer, he's saving labour, he's getting in out of the job faster, and it's not going to go wrong. If it goes wrong, it's our responsibility, and so he can move on to the next job and make profit. Cost to whom as well? Is it the owner of the house? He's going to have better efficiencies forever if the coldest water is going back to his condensing appliance. If his mixed temperature is going to be mixed because there's no conflict with any other zone, he hasn't got this conflict as was described by the original diagrams in the very first slide. So all of the characteristics that should be in a heating system are matched here, as far as I can see, extremely well. And any job we've ever seen, I've never seen a job with an issue that to do with the concept of the system. So maybe one will come someday, but I've never seen one up to now. So it's a very positive thing to bring into any job that you're doing. You put it in, you walk away. So you can have multiple zones, and again, if you're going to have these connections and you're going to buy T's, for every T you have 3 joints, you have to cut bits of pipe and making joints and trying to figure out how to get them together and looking at neatness and trying to get them packed into a corner or whatever. With this, you put it in, it's done. It just makes sense. Now here we look at, so what I was saying, you mentioned roughly earlier, where you might be collecting heat into a manifold, say from 2 boilers. You have your pressure vessel connected onto your neutral point. You might have your filling point in here. And now your high temperature water is taken directly to a high temperature unit, such as a calorifier or heat cylinder, domestic water cylinder, whatever. Whereas you might decide to take a circuit from the right hand side and put that through a mixing valve, so you can have a controlled temperature leaving to the second manifold, and then you can divide that down further again with more mixing for say underfloor on zones B1, B2 and D1, D2, whereas you can have full temperature on zones A1, A2, C1, C2 and also on R1, R2 with even a return come back if you wished on the middle. It doesn't matter because all that water is going to be drawn down here in any case. So combining units is not an issue. Now we look at a couple of kind of more, we're talking here about how easy it is to control. If I have our Interlinking wiring center, which will accept any form of control, analog control into the thing, so we can have our radio receiver connected onto it, our hot water time clock or whatever. Then we have our radio stats for the upstairs radiator zone signaling back. That is converted into a pump control circuit that feeds down and turns on the respective pump to cause the radiators to heat, or the downstairs circuit to heat, or the hot water to heat. So combining the control concept with the zones is just, again, very simple. I'm showing that this is radiator zones and with radio, but of course it can be hardwired just as easily if you wanted to do that. Now with this scenario, we're looking at having a solid fuel appliance. People say, I won't ever be doing solid fuel, I have no interest in solid fuel, I don't care about solid fuel. But I'm saying to you that if you can understand solid fuel and you can understand the principles of gravity circulation, you're already on a winner. Because to understand how that works without assistance of pumps, you have to understand pipe sizing, gravity circuit, deaeration, because it doesn't have all these modern fandangos to get rid of all of the issues like boilers that deaerate themselves and whatever, and also pumps that regulate themselves. So in this scenario we have an 100% open circuit from the solid fuel appliance to the hot water cylinder. Let's follow it. Flow comes up, goes through the manifold. You already know there's no obstruction, travels across the top chamber, goes over the top chamber, round through the bypass, completely open, no resistance, and it gets to this point. You'd imagine it has two circuits it could take to get back to the solid fuel, because it's trying to fill this area. There's something I want to say as well, it's very important. Many installers have the impression that solid fuel wants to form a circuit. It doesn't. It just wants the hot water to rise to the top. Hot water by its nature will want to rise above colder water. As it rises up, any water that's there that's colder will be pushed away and pushed down, and the cold water, as it loses more heat through a cylinder, or as it's on a longer journey, will lose more heat and it'll tumble back down. So the hot stove just simply wants to get water up to a top level, and then your circuit must be designed to take away that heat and let it fall back. So when it gets to this point, if it tries to go through the pump, there's a non-return valve, so there's a resistance. It's not going to be able to flow there. But if it takes down through the center of this T, it's falling down, it's trying to get back to the stove, but on the way down there's a heat lock loop. The reason for this heat lock loop is actually quite similar to the reason for a non-return valve over here, which we'll talk about separately, is so that any heat that's in the cylinder, heated by the gas boiler, by an immersion, by the solar or whatever, is not going to be drifting back out and drifting off up and being lost in the house, which is a colossal waste of energy in the vast amount of installations that there's utterly no need for. So this heat lock loop dropping down below the cylinder and rising back up goes into the coil. Now it meets the cooler water in the cylinder. The heated water in the coil is cooled, it becomes more dense, it falls down, and it falls down into the center of this injector T right down here. That injector T will allow for the water to go in the middle unobstructed and back to the stove. But there's a little spigot sticking out here that if this pump turns on, it fires water past the center connection. Using a principle called the Bernoulli effect, it sucks water back out of the center connection, so it assists the gravity circuit, and at the same time it fires the water from the manifold, from the energy zone, down through the injector tree and into the stove. That picks up excess heat, and then the radiators will have water. The pipe stat that's located at on the return from the cylinder is critical. It's set at 55 degrees. Why? It's set at 55 degrees on the return because you should never let water less than 55 degrees get into a stove if you can help it. Obviously there's a startup period and there's a cooling down period, but I'm saying that in the normal course of events you want to have it so that the pumps will draw the cold water back from the system only when the return going back to the stove can handle 55 degrees. There's two reasons for that. One is the back end burnout, where the stove will form acidic flue gases, will condense onto the surfaces and damage it. But the second is you want to keep your flue gases hot enough so that they'll convect out of the chimney and away. If you take too much heat out of the stove and the water is cold, the smoke will have no potential to rise. If it has no potential to rise, it can lodge in the flue on the way up or start to drift very slowly. The stove will need to be able to move heat through it so they can get fresh oxygen to get at the combustion process. And if it's restricted because the smoke can't get out, the oxygen can't get at the combusting fuel, and instead of forming carbon dioxide and water vapor, it could form monoxide. Very, very dangerous. So the pipe stat is critical, that it doesn't let the stove turn on too soon. That can obstruct itself with its flue emissions and cause the system to be quite dangerous. If it's done properly like this, it is a really, really comfortable and a fabulous addition to any home, because as I have always said, have you ever tried to sit next to a heat pump for comfort and read a book? You sit next to the fire's delivering heat around the house. It's just a lovely addition to a house, and if it's done properly, it is so safe. In fact, if you listen to what I just said, there's more thought put into the safety side of solid fuel than would ever be put into any other form of system, because it has to work by nature. So we've gone through our cold feed coming down, having reached the correct temperature, the injected water coming from the energy zone coming down and causing the radiators to circulate, and then we have a control mechanism that pulls turns on the respective zone pumps as you would need, but that's not what this talk is about. There's one other thing. The open vent is taken from the exact place it should be, where there's a pipe just at the air trap where it completely vents the entire system. But the cold feed with solid fuel should always be taken as close as possible to the stove. Now, what would cause water to have a momentum to go from the cold feed to pitch out the expansion? Well, it has to be affected by a pump, unless something is boiling. If it's boiling, then you have an open expansion, so it's supposed to pitch out the expansion pipe, and also has a safety valve. But in this scenario, what it has very simply is that the cold feed is onto the return pipe, no pump, on the flow pipe, no pump, coming through the manifold, no pump, onto this bypass chamber and out to this T, no pump down through the cylinder. So it's completely without an impetus or a forced impetus like a circulator that would cause any momentum that would cause it to pitch. So because it's piped this way, the system will not pitch unless it has reached a danger temperature, and then you want it to pitch to get rid of the excess energy from the system. The gas boiler in the meantime is not coming from the middle chamber L2 or from its equivalent R2. It's actually taken from R3, and R3 is the coldest water come back from the zone. So the gas boiler is working at these grand condensed low temperature circuit temperatures, and the solid fuel is working up at these high temperatures, both exactly in accordance to what manufacturers say they should be doing. NRG Zone so can draw away the heat from out to the underfloor or down. I'll just show with the mixing valve on the underfloor here, and it'll be drawing water across. If the mixing valve needs to open the port to allow heat to be drawn from the unit, there's no pump at the unit. If you look for underfloor heating, the pump is at the manifold only, with this particular type manifold I'm saying. And at the same time, the if it is up to temperature and there's sufficient heat to be circulated in the floor, now this pump has no conflict. It can circulate within the mixing valve bypass circuit and pass around out to the floor. So you've got a very rapid heat up time, a very fast underflow situation. Now we're going to look at a system, and if you can follow this system, I believe this talk will have been very effective, because we're going to look at what would seem to be strange. You might never have need for this job. We've used it in a number of times and it is extremely good. But what I'm trying to say to you here is, look at what you can do. If I have two heat pumps and I want them to be able to heat a low temperature coil in a cylinder for preheating purposes, if this boiler is underneath, you remember what we said a while ago, they can draw water from the cold chamber and put it into top chamber, and this pipe here, A1 and A2, that's connected to the top chamber, so that can take the heat down and it can heat the cylinder. So the heat pumps just on their own can operate away and heat the cylinder, if you have night rate electricity or whatever, to preheat your calorifier, whatever size calorifier you might have, to heat preheating, right? At the same time, if the gas boilers decide you want a full temperature, they do exactly the same thing. They take the heat from the cold chamber, push it up the top chamber, and this pump takes it down and heats the high temperature hot water. So if you use this system and this system, you can have preheating and high temperature, where the gas boilers can modulate. Obviously you have it wired so that it won't be taking all of the energy if the coils in the calorifiers can't actually take the heat. But who knows, you might have a very large heat exchanger or a DHW system that has a big enough heat exchanger to take all of the heat and prioritize the heat. But if I now want to heat this manifold, which is, we've got a NRG 4 because we're heating just two gas boilers, we're using the side connection, NRG 5 because we're using one of the side connections, one of each side connection, and we have a circuit going to the low temperature cylinder, and then we have the two heat pumps, and then NRG 6 because we want to have a mixed temperature circuit, a second mixed temperature circuit, two full temperature circuits, and two underflow circuits. Now we've got 6 zones off this manifold. What have we got? So we have heat pumps that can do preheating on the hot water. We have gas boilers that can preheat the hot water, or can heat at full temperature. But if we ever turn on this shunt pump, and that will turn on very simply because one of those zones here is calling, the coldest water coming back from the heating system will be put through the bottom chamber of the NRG 5. If it is, it'll be taken by the heat pumps and put up to, let's say, 45 degrees. At 45 degrees, it's delivered because this pump has no other choice. It can't find a circuit here to get anywhere else. It can't go through the cylinder circuit, can't go anything unless this pump is running. So its only choice is through this non-return valve, through to here, and it wants to get back to this pipe. So if the gas boilers were not on, the heat pumps could be just heating this zone because it'll come to here, go through the bypass, cross here, out through that, and back around. So now the heat pumps alone can heat the heating system if that's what the system design calls for. If in the meantime you want to have the heat pumps preheat the heating water, the heat pumps fire up to say 40 degrees and brings up to 45. The cold water or 45 degree water is put in here, drawn down by the gas boilers and taken up to whatever you've decided your delta T is to be. Let's say 70 degrees. Your 70 degree flow is coming off out. And now this pump's momentum pushing water to this enclosed circuit is pushing the 70 degree water over. So now we've got a full temperature circuit. So look at the options. We can have preheating on the hot water with the heat pump, full temperature on the heat pump independently. We can have the two of them operate absolutely together but separately without heating the zones. And by simply turning on this pump because one of those zones are calling, we can have the heat pump preheating the gas boilers, and that's heating the hot water if this pump is on, and heating the heating system if this pump is on. So we have all of the cakes we want to eat, to enjoy and have and eat all at the same time, if you can follow me. We've got every attribute that a proper system should have with regard to energy efficiency, with regard to safety, with regard to neutral point creation. Again, our pressure vessel could be introduced here. I would suggest that's a good idea. It could also just as easily be introduced here because that pipe is connected by an open path directly to here. I would think this is probably the best place. The cold feed could be brought in here. It could even be brought here. Where I'm showing it is brought in up here. So very, very versatile. If you can follow this particular drawing, then it's been worth your while watching the full lot of what I've had to say, because that really is the understanding that's needed. That the fact that you have so many options to do so many things. The Interlink zone is the equivalent for wiring as the energy zone is for water. The power is brought into the power supply, 5 amp fuse. It feeds 4 1 amp fuses. Each zone for a clock or stat or pump or whatever is protected with its own 1 amp fuse completely independently from zone 2, 3 and 4. Each of them have an LED telling you that the particular zone is calling. There's 2 relays. The boiler relay has a double pole switch which can operate a boiler or 2 boilers. They're volt-free contacts, so you can use them for switch lives or volt-free. Each boiler has a 3 amp fuse. So boiler 1 has a live and neutral, boiler 2 live and neutral with 3 amp fusing on the lives, and there's a 3 amp control for if you want to have one common control for everything. You can feed it from here. Completely separately over here we have an auxiliary relay, and we have auxiliary inputs. We also have auxiliary power supply, all fed from a separate 3 amp fuse as well. If I put power into any one of those 4 auxiliary inputs, which are in series with connections directly above, so if this is connected to that, that's connected to that, and so on, that's connected to that and that. So if I put power in here, any one of the 4 inputs will not backfeed with any other, but will close this relay. If that relay closes, the common will join from the normally closed to normally open here, and from the normally closed to normally open here. So now I can use that for additional zones, additional boilers, for auxiliary functions like hot water priority. It's way too much to talk about in this, but I'm just introducing it. There's also a phrostat that turns on the boilers but bypasses the zones. But you can also use this as for functions, but if you want to turn on the boilers for who knows, because if you have an auxiliary function doing something and you want to turn on these boilers, well, you simply go into the phrostat and put here. The one thing I will say to you is the 4th terminal here at the top. So there's this is A. Again, if you remember our numbering back with the energy zone, there was A, B, C and D. This is electrically A, Zone B, Zone C, Zone D. So I would strongly suggest that if you were using the energy lex with the energy zone, that you keep A's together and B's together and whatever. So if you're looking at the 3rd pump, it should be wired from the 3rd fuse and the 3rd circuit here. But the 4th terminal here, if power ever arrives, having left the clock, gone off out to your cylinder stat or room stat, come back from the cylinder stat or room stat and arrives here, 3 things happen. this light lights. The fourth terminal is joined to the fifth and sixth terminal. So if you have a pump connected to there or a motorized valve, the valve will open or the pump will run or whatever. And then, as well as that, through an electronic process, this relay will close. So it's the only terminal you ever have to learn that really matters is the fourth one here, the fourth one here, here and here in A, B, C and D, because they're the ones that do all the work. The rest of them are just connections, a connection for power, a connection for your pipes, for your pipe stat or room stat, and a connection back to operate your pump or your time clock as well. Connections are here. So if you can understand the four connections here, so it would be A4, B4, C4 or D4. You also understand that this is the equivalent auxiliary input, auxiliary A1 or 1A, I think, 1 and then 2A, 3A, 4A. And what that means is that if I can understand that any one of those four inputs here cause that relay to close, and any one of those four inputs here, the A1, A4, B4, C4 and D4, close that relay, now you can understand we've got a very, very simple process to control it. Of course, we've got earth blocks on the board as well, so it makes it extremely easy to logically sort out very, very neat wiring. So when you look at how that might be applied, you take your, I haven't shown the detailed wiring, but let's say for instance you have clocks and stats or whatever here, that zone would operate a given pump. The second zone wiring wise would operate second pump, third and fourth, so on. The power supply for a boiler would come from the power supplies coming in this line here on this one, and then the control for the boiler would come on this line and come down and operate that boiler, and separately from the second switch will come down and operate that boiler. The auxiliary could be saying that if you want hot water, that you want to turn on the boilers but you want to do some auxiliary function, you can take your power supply from the auxiliary fuse, go through your hot water stat and then turn on the auxiliaries to do whatever you decide you want to do with your auxiliary relay. Again, there's too much to go through in this short explanation. So the units, we've seen standard size units, but if you look, we make all sizes. For example, here's the one where there was an original boiler house that had, I think there's 3-inch connections on the far side, 75mm pipe, and the boiler was connected, originally was connected from here to here, so we intervened by putting in the manifold, but that then gave us an opportunity to put in condensing boilers here, where we have 2 flows, 2 returns, but we also then have a shunt opportunity with extra connections for the way the job was done. And it also, if you look over here, we have temperature sensor here, and we have temperature sensor connections at different points, so we can actually, and temperature connections on the top as well, so we can use it for our building management system to get very, very accurate, clear points for locating whatever strategic temperatures we require for the job. Here's just a simple enough unit. It has 50mm connections on the left, A1, 2, 3 are 50mm on the right, and then there's 10 zones, each 28mm. It just made a very awkward job extremely simple. This job was used for a log burner on the left, very large log burner from a buffer tank, and then on the right 2 condensing boilers in parallel. So very simple job. Because we make the manifolds and we also make panels, and if you look, this particular panel needed a flow temperature sensor, bypass temperature sensor and a return temperature sensor. The reason was because there was high temperature and there was a heat pump as well, so the control was going to make a difference of what boiler would come in, what appliance would come in, when what zone is called. But again, when we make our panel, we make the MCBs in the panel and the LEDs on the doors and everything, all the wiring, the fusing logic, all comes together to match the numbering of the zones, so that if someone's looking at the manifold and they want to figure out where's the control wire for the 4th zone, it's D. If it was the 3rd one, it's C. So again, very straightforward, logical. So this is a very interesting job in a large supermarket. It was air handling unit, so we made this containerized unit with 415 kilowatt boilers, wall hung boilers. They go into a large manifold, each with its own circuit down onto separate air handling units, and there was overdoor units and whatever. And then there was also hot water control inside the unit. And just round the corner here, you can see the side of here was our control panel. So this was just dropped onto the roof. The pipework was prepared in advance, and then it was a really rapid exchange. The system was completely connected in 2 or 3 days, in and out. So very fast. It's been there for years, never a callback, just working absolutely like a dream. So what have we said? We said that the NRG Zone speeds up the process. There's no callbacks. It's easy to understand. It's easy to design. It reduces the cost of installations. There's connection points for not just for zones and boilers, but also temperature sensors and the like of that. It greatly simplifies the design. If I draw a rectangle and I put another rectangle called a boiler to the left, to the right, above, below, whatever, and I connect it to the right thing, I'm off. And then if I go to my connected for cold feed and expansion, again, there's very logical reasons why they would be connected to where they should be precisely connected with every system. The expansion and filling points are also likewise just what I described. They're perfectly placed onto the system neutral point. Unobstructed bypass, don't take that lightly, because people talk about putting in bypass valves and putting in diverter valves and figuring out when would the diverter valve not be affecting the temperature of the return water. Here we have a completely unique way of going about it that just allows the diversion or the bypass to do exactly what it's supposed to do without compromising the system's efficiencies. So you've seen multiple examples where you can have a manifold collect heat or heat sources and deliver to other manifolds. We've got one job where we have one major boiler house delivering with a major manifold with 7 zones, each of them going to 7 independent buildings. Each building has its own manifold, and some of them their own heat sources onto the other side of the manifold. So it just means that we can make it an extremely complex job very, very simple. Then we have the dynamic flow and return bypass will allow water to flow downwards, which of course makes sense if you're coming from the flow, but also there are times when you need it to flow the opposite direction, so it allows for both directions being such a broad opening and the way it's strategically constructed. So connection points for all the heating zones, and I've shown you can take them in certain situations from the left, from the right, from the top, from the bottom. Just it depends how you go about it. And again, just to repeat, you can only connect the flow onto where the boilers are delivering the heat into, and you connect your return back to the chamber that the boilers are returning back from. And then the water isolation, we've mentioned that with the buffer tank. We've spoke about stratification, but the hottest water is contained as it passes through and drawn away for zones and whatever, and the return water is also captured and in a stratified position where it can be drawn back by whatever appliance you've decided you wanted to let it be drawn back to. And then the built-in air separation. Air is the arch enemy of heating systems. If you get rid of the air from the system and the system is circulating properly, you're going to find that the gunk that is so prevalent in so many modern systems just doesn't seem to build up at all, because the air is what is the source of the vast amount of that gunk. Every single time the water passes through this manifold, it's being deaerated in an extraordinary way with an elongated chambers catching every tiny minute microbubble and forcing it up, allowing it to drift to the top. Certainly when the system stops, any air trapped in those spaces will migrate to the top, and even as it's operating, they're being directed towards the air trap. So uniform temperature to all circuits, we're back at square one. I said to you that we have a lot of systems where you come across systems where the flow from the boiler can be undersized, and people like Caleffi and Takeo, and they have different drawings, all say you must have a proper header size, you must allow for the volume to pass to reach all the different zones. With this scenario, we've got an extraordinarily large area inside, even for a small domestic situation. We've got an extremely large chamber on the flow and on the return that gets rid of all of the hassles with not having uniform flow to every circuit. So problem solved. And then the last thing I didn't mention is that standard units come with 25mm thick high density insulation, and if your pipe are connected to the manifold is as good a quality as that, you're going to have practically zero heat loss where there shouldn't be heat loss, and all your concentrated energy will go where it should go to, out to deliver heat to where it's needed, and increasing the efficiency of the system again dramatically. So hopefully you enjoyed that. Hope it wasn't too long, but I've taken you right through from top to bottom on the basics of the system, and we've gone into some of the more complicated applications. If you followed it, brilliant. If you have any questions, please contact me at info@nrgawareness.com. So info@nrg, the letters, not the word, awareness, awareness.com, and I'll be delighted to help you with any of your queries or questions. And you do know we provide a design service, a free design service for normal type ordinary situations, and if you have a very complex job that needs a lot of assistance with pipe sizing and radiator sizing, whatever, we provide that service as well. Then we can negotiate a fair price to make sure that you get an opportunity to make the profit that you should be making on every job. So again, thank you so much for your time. I'm very grateful. I hope you enjoyed it.